I'm just going to draw an analogy to a distribution in space. So an analogy for 3 or more dimensions in which, as I've said, we don't have just one tangent vector. In 3 dimensions, if we have a 2-dimensional surface, we have an infinite number of tangent vectors, we have a tangent plane. Okay, so first of all, in 3 dimensions, let's say we have a function t of x, y, z, and instead of a curve, a surface. And let that surface be given by some function f of x, y, z equal to some constant. And in general, we could bring the constant over on this side. We'd still have a function f of x, y, z if we were to subtract our constant. So it would be f of x, y, z equals 0. And we want the maximum t on that surface. Now, the surface might be a quadric surface, might be a sphere, might be an ellipsoid, a hyperboloid. It could be any kind of a surface, any more complex surface. Now, suppressing a little bit of the notation just for the moment, normal vector to surface f of x, y, z is constant is just the gradient of f. And the condition that the gradient of t be parallel to the normal vector then becomes a condition for maximum or minimum. Condition for relative max or min is just that your gradient vector delta t is parallel to your normal vector. And that's, I don't know if I left myself enough room here, del f. Yeah, we kind of got it on there. Might be a little hard to read, but we understand. There's your normal vector. And delta t, or del t, your gradient of your temperature function, has to be parallel to your normal vector, which is the gradient of your f vector. Now, in 3 dimensions, it's of course possible to have just a curve instead of a surface. So if we have a 3-dimensional situation where we have t of x, y, z and a curve, which can be described by a position vector r of t equals x of t I plus y of t j. If I have room, I'm always running out of room, plus z of t k, have to slip that k in down here, but we should understand. Then you have a maximum temperature on the curve when what? Well, now we have a curve, we have a normal vector. That occurs then when the gradient of t is perpendicular to our unit tangent vector, or the gradient of t is parallel to the normal vector. I'm not sure if I just called that unit tangent vector, but that's just a general tangent vector. So that in any case, the condition that the gradient of t be parallel to a normal applies whether you're talking about a normal to a surface in 3 dimensions or a normal to a curve in 3 dimensions.